So in this video, I wanted to use all the things we've kind of done and analyze the function. And then at the end, we're going to look at the function and just make sure our analysis is correct. So let me start by getting the first and second derivatives written down. Okay, so in this case, g prime of x would be 4x cubed minus 24x. If I do a little factoring, I could take a 4x out and I'd have x squared minus 6. The second derivative, g double prime, is 12x squared minus 24. If I took a 12 out, I'd have x squared minus 2, like that. So the critical points are whatever makes the derivative 0 or undefined. So right here, 4 times what is 0? Well, 0. So x equals 0 is a critical point. And what squared minus 6 is 0? Well, the square root of 6 squared, and the negative square root of 6 squared. So I have both of them. Now I'm going to do a little bit of sign analysis. I'm going to do it right next to that, okay? So we're going to have negative square root of 6, 0, and square root of 6. And I'm going to kind of quickly fill out the signs of this, okay? If I plug in a big negative number, 4 times a negative is negative. A negative squared minus 6, a big negative squared minus 6 is positive. So negative times positive is negative. If I plug in a number here, negative square root of 6 is negative 2 point something. So maybe plug in like negative 1. 4 times negative 1 is negative. Negative 1 squared minus 6 is negative. Negative times negative is positive. Number between 0 and the square root of 6, so maybe 1. 4 times 1 is positive. 1 squared minus 6 is negative. So positive times negative is negative. Finally, a big number, maybe 10. 4 times 10 is positive. 10 squared minus 6 is positive. So this is positive. So I'm going to write some justifications and then we'll get the intervals. The function is increasing, remember, when g prime is greater than 0, and decreasing when g prime is less than 0. So that occurs from negative square root of 6 to 0, and from square root of 6 to infinity. Decreasing from negative infinity to negative square root of 6, and from 0 to the square root of 6. Okay. Well, we have local minimums when the function changes from decreasing to increasing. So f prime, or I'm sorry, g prime in this case, get my function right, g prime changes from negative to positive. Well, that occurs when, or at negative square root of 6 and at square root of 6. Now I'm putting this in a point. I could have, if all I said was where is the local minimum, I just would have said, oh, it's at x equals negative square root of 6 and square root of 6. But I thought it would be useful to actually get the y coordinates and tell us, here's the point that's a local minimum. Well, if I plug this in to the original function, and whenever we want a y value, we've got to go to the original. The negative square root of 6 to the 4th is the same as 6 squared. It's 36 minus 12 times 6. So 36 minus 72 is negative 36. Okay. Because of the signs here, because it was to the 4th and squared, plugging in positive square root of 6 is going to get us the same exact answer. You can check that, but it would give us negative 36 as well. Local maximums occur when g prime changes from positive to negative. The x-coordinate is 0 where that occurs. And if I plug 0 back into the original function, 0 to the 4th minus 12 times 0 squared, I get 0. So 0, 0 is the maximum. All right, now I'm down to inflection points and concavity. So now I'm going to analyze the second derivative. So maybe just to keep these straight, I should go up here and say this was the analysis of g double prime, or of g prime. Down here I'll do a little analysis of g double prime. So looking at what makes g double prime 0, of course nothing out here because it's just 12. What's squared minus 2? Well, the square root of 2 and the negative square root of 2. Now, I can't say they're inflection points yet. Okay, up here, when we found the zeros, we said, oh, those are the critical points. You can't say it's an inflection point until we prove that g double prime changes signs. So we're actually going to have to do the sign analysis first. So let's do that. If we plug in, a negative number here, we get 12 times a negative number squared minus 2, big negative number squared. It's going to be positive. If I plug in like 0, 12 times 0 squared minus 2 is negative. And finally, if I plug in a big positive number, 12 times that number squared minus 2 is positive. So those are inflection points. And again, we could actually get the coordinate. I don't know that we would really need to, but it's good practice, so let's just do it. If I plug this into the original, remember, whenever we're trying to find a y coordinate, we have to go back to the original. Square root of 2 to the 4th is the same as 2 squared, so 4 minus 12 times 2, so 4 minus 24 is negative 20. And we get the same thing here. Okay, so now we go to concavity. We're concave up when g double prime is positive. Concave down when g double prime is negative. So positive from negative infinity to negative square root of 2, and from square root of 2 to infinity. And we're concave down from negative square root of 2 to positive square root of 2. Now, I'm going to show you what the graph looks like, and we're going to verify this. Again, we're just looking for kind of maximums at 0, local max at 0, 0, minimums. We're looking for it to be concave up, concave down, kind of in the middle. So let's look at the graph. Here it is. So again, we had our local minimum. There it is, about negative 36. Square root of 6 we said was between negative 2 and 3. Another local minimum here. Local maximum at 0, 0. We had said that the inflection points were at about positive and negative square root of 2. That's about 1.4. So you look at those points, and doesn't it look like that's where the concavity changes? It's concave up, then concave down, then concave up. So what we did with our derivative checks out with the original function.